Thank you very much. Thank you, Thomas. Thank you, all the organizers, for the wonderful invitation to this. I'm glad I'm finally making it to this CNQM series of workshops. So after this musical introduction, vaguely inspired from Game of Thrones, I'm going to try to convince you that winter is not coming for the Hubbard model, but rather spring. So let's see if I can do a good job. So you see the advantage of this title is that although it's a little pretentious, you can use it over and over again. The only thing you have to do is change the date here. So maybe I should have called it 2 or 3 things we know about the Hubbard model rather than what do we know. I'm not, of course, going to be able to cover the whole spectrum of things we know. Okay, before I do anything, this is not working. Got it. Okay, I don't know why this is not working. I'm going to do it like that. It's not working either. Okay, this is back now. Okay, before I do anything, I would like to express my really warm thanks to a number of collaborators with whom I have worked on these and related models over the last few years. And many of them are on these slides. I'm sure I forgot some important ones, but thank you to really all of them. I think there is no need to remind the audience what the Hubbard model is, but just to set up notations. We have electrons with spin half hopping on a lattice. And when it comes to the hopping term for a large part of this talk, this is going to be nearest neighbor only. But once in a while, I will mention the crucial effect of TPrime in the course of the talk. There are obviously many reasons to study this model. We would like to understand its phase diagram in parameter space. Parameter space is obviously the coupling U over T, density per site between 0 and 2, the difficult region being obviously around half filling, and temperature, which, as you will see, is an important parameter in particular when it comes to computational methods. So why study this model? I don't need to convince the audience, but just to recall you some of the basics. It's really an iconic model. It's one of these models which is perhaps not realistic for an overwhelming majority of materials, but captures some of the essential qualitative physics. As I will try to convince you, it does capture, in my opinion, some of the very basic qualitative physics of the cuprate materials. Of course, many other materials are multi-orbital, and this is a whole field, but the cuprates are kind of exceptional with a couple of others. It's also important in the context of cold atoms, although fermionic cold atom platforms are still a little hot. I think there is good hope that a new generation of experiments is coming online, which is going to be able to reach the temperature regime, where, as you will see, interesting physics comes up. So I think this is an increasingly important motivation to study this model. But the really important thing is that it's playing the same sort of role conceptually than the Ising model is playing in statistical mechanics. It's the archetypal model of strong correlations. So it's very important to our field. Okay, so the main message of the talk, and some of you may want to go to sleep after that slide, is that I will aim at convincing you that there's really been tremendous recent progress in our understanding of the 2D Hubbard model, especially thanks to putting together a number of different computational approaches to address the same physics, and especially to address the same physics by looking at the same region of parameter space with different points of view. The different points of view do not stem from the fact that we are not confident in one method versus the other, but rather that by combining these different points of view, we can actually unravel much more of the physical reality of this model. And in particular, there's been really a handshake between different types of methods that I will briefly review in the following slides. So that's more or less the outline of the talk. I'm going to tell you a little bit about the methods. Then I'm going to focus more on ground states, and especially on the question of the infamous competition between stripe ordering and D-wave superconductivity. And then I will move more to finite temperature effect, especially the famous pseudogap, tie it to the physics of emerging spin correlations. And I will conclude the talk with reporting on some recent results that allow to answer a long-standing question of the field, namely what is the fate of the pseudogap state when you cool it down to low temperature, at least in some regions of times. Okay, so this is a key slide, the talk, where I try to express the notion that progress in this field has been realized by a handshake between different types of computational methods. And computational methods are not black boxes that you just run and watch the results. They are rooted in concepts. Every single type of family of algorithm is actually rooted in a physical picture of how to address a system. So there are two important classes of methods on this slide. One have been for a long time limited to 0 temperature, and they are based on the concept of entanglement. As you know, many-body quantum states can have a very large degree of entanglement. A typical state may have volume law entanglement, which makes it very difficult to address computationally. But the ground state and the low-lying excited state may have, in favorable cases, a lower degree of entanglement, perhaps with area law entanglement. And that has allowed to use very efficient compression methods to represent these wave functions. This, of course, goes with matrix product states method and tensor network methods on which algorithms like the density matrix normalization group algorithm can be applied. So the organizing principle of these methods is entanglement. And these methods for many years were limited to 0 temperature and ground state studies, but a very significant evolution of these methods in recent years, as you will see later in the talk, has now allowed to put to good use these approaches to access finite temperature. So this is really going up in this direction in this parameter space. At the other end of the spectrum here, perhaps in the high temperature regime, we have methods that leverage not on the principle of low entanglement, but on the principle of locality. If you go to high temperature, but that would also apply if you go to large doping or perhaps other regimes of parameters, correlation length for any type of incipient order in the system become relatively small. And you can then build approaches that are based around the concept of spatial locality. The sort of iconic version of that is dynamical mean field theory. If we are talking about the two-dimensional Hubbard model, single-side dynamical mean field theory is, of course, insufficient because correlation length grow rather rapidly as you go down to low temperature. But cluster extensions of dynamical mean field theory can be put to good use there and allow you to make your way down in energy scale. So here, there is an interesting region where first, there is interesting physical action. And second, these different types of methods following different conceptual routes can merge. This is what I call the handshake between different methods. And this is what is currently, in my opinion, really transforming our field. On top of that, there is a third class of methods. This slide is making the point that one of the challenges to make these different classes of methods to talk to one another is the fact that those methods are based on wave functions. Those methods are based on Green's function, which are much more compact way of expressing observables. So one of the challenge in realizing this handshake is to make sure that despite the fact that they compute different quantities, they can still talk to one another. There is a third class of method, which is sort of approaching the problem perhaps transversally like that. And these are all the Monte Carlo method. And right now, there's been a lot of progress with two classes of such methods. One is the so-called projective auxiliary field Monte Carlo, which I'm not going to describe very much in the talk, but I'll use some of the results. And another one, which I'll talk a little bit more in detail, is diagrammatic Monte Carlo. Diagrammatic Monte Carlo is a method that starts from a rather surprising premise, which is to be able to access non-perturbative regimes by actually summing up the perturbative series. At finite temperature, the perturbative series is convergent. It has a finite radius of convergence. And by using various tricks, one can try to push this radius of convergence to large enough value so that converged and controlled results can be accessed for values of U over T, which are no longer in the weak coupling perturbative regime. So it's doing non-perturbative physics with perturbative methods, thanks to resummation methods when it's actually possible, both to generate the series and then to sum it up. And this is a method that has undergone tremendous progress in the last few years. And one of the virtues of these methods is that it addresses the problem directly in the infinite volume thermodynamic limit, in contrast to DMRG, for example, or in contrast to cluster DMFT, which requires an extrapolation to large cluster size. Okay, so this was just to draw a landscape of the various methods that I'm going to sort of use in combination in the rest of the talk. And as I mentioned, progress in this field has been made possible by recent papers for the last, say, 10 years that have combined these different methods together. These are just some examples. The Simons collaboration on many electron problem has played a big role in putting together a number of authors to that aim. Okay, so let me start with ground state. So what do we know today about the ground state of the two-dimensional Hubbard model with, say, T' equals 0, just to start modestly? So this is a phase diagram as a function of U and whole density away from half filling for 0 temperature. And this phase diagram is actually not intended to answer the question, is there superconductivity? This will come later in the talk, but it's just meant to separate two regions, one region in which the ground state has both spin and charge long-range order, and one region where there is no such long-range order. Near this boundary, there may be some region that has also superconducting order. I'll address that in a minute. So this phase diagram was established in this paper, which uses mostly auxiliary field quantum Monte Carlo. And you see here that there is a boundary such that at a given U, say here, there is a finite critical doping below which the ground state is indeed stripe ordered and above which it's not. And please look at this boundary because it will play an important role in the rest of the talk. So what is stripe ordering? Stripe ordering really is the fact that there is a modulation of the spin density, which is here the red line. And what is depicted here is the prototypical stripe at 1/8 doping in that case, in which the charge wavelength is 1/over doping. The spin wavelength is actually twice the charge wavelength. You see that the hole likes to actually stand where the spin density wave has a node. This is not to say that this is the most favorable stripe order, which is always picked for all doping and all T prime. but for T' equal to 0 and 1/8 doping, this is the guy which is the most stable, I think. And you see this modulation, you see here in real space, so this is X and Y in this geometry, you see this modulation as well. So stripes are not particularly new. In fact, I consider it to be a triumph of just unrestricted static mean field or Hartree-Fock theory to have predicted back in the day, very early on after the discovery of ITC, that stripe ordering would take place in the ground state of the two-dimensional Hubbard model. There are many beautiful papers by a number of authors from 30 years ago that have documented that. One of the ones that I like particularly is this beautiful paper by the late and much regretted Heinz Schulz. This topic of doing a good job at Hartree-Fock descriptions of the ground state is actually not over. There's been here in Walter Metzner group a very beautiful set of work from which I extracted this phase diagram, which has completely clarified the structure of the Hartree-Fock ground states for the Hubbard model. So what you see here is that from a Hartree-Fock point of view, there is a region of pi Néel order, which eventually turns incommenserate in that green region, and eventually charge ordering sets in, and there is stripe order. And this is very generic. This is what happens from a number of computational results. In fact, all computational methods currently agree that there is stripe ordering in that regime of the phase diagram at low doping and according to this boundary, including, for example, single-side dynamical mean field theory when done on an unrestricted way on the lattice. And this is a very beautiful work that I had somewhere. Well, I didn't put it here, but there is a beautiful work from which this is extracted, which is due to Peters and Kawakami, who have studied this with single-side DMFT at 0 temperature using NRG solvers. Okay, so now you all want to know about the burning question. Stripes are good, but what about superconductivity? And I will try to do a reasonably fair job reporting on what we know and what we also don't know at this stage on this topic. So a couple of years ago appeared this paper, which is entitled Absence of Superconductivity in the Pure Two-Dimensional Hubbard Model. Absence here is an important word, and pure is another important word. So pure here, perhaps not the best adjective, is meant to mean T' equals 0. And absence is absence in most of the parameter space that was explored in that paper. And as you will see, there is still room for some discussion in some corners of that parameter space. Okay, so what everybody agrees also is that in the two-dimensional Hubbard model, there is a strong tendency to superconductivity. What does that mean? This means that if you put a small pairing field, so if you trigger the pairing by putting a little field that is conjugate to the pair creation operator of D-wave type, the system responds strongly in some regime of doping temperature and U. This is ground state, this is 0 temperature. And you see that. This is the response of the order parameter to a small pairing field as a function of doping. And you see here that there is a dome in doping where the system responds strongly to such a pairing field. Now, and we've known that for many years, from DMRG, from cluster DMFT, from many different methods. Now, this is not the end of the story, because the fact that the system responds strongly doesn't imply that this is the order that wins in the ground state. So this is a much more delicate question, and this is where the recent progress has been taking place. It is an incredibly delicate question, because the energy differences between the stripe order ground states and these states with incipient superconductivity are incredibly tiny. They are of the order of 10 to the -2 in units of the hopping. And also the difference in energies between different types of stripe patterns of the same order of magnitude. So in this paper and a few others, there was a very systematic combination of methods, taking very carefully the question of boundary conditions and so on to actually assess this competition. And what was concluded is that in most parts of the phase diagram, when T prime is 0, there is no superconductivity does not win in the ground state. If you look carefully at that paper, however, this one here, you will see that there is still some region of the phase diagram which is not entirely, in which there is just no data point or where the competition was not entirely settled. This is roughly speaking in this region near the phase boundary. And in my opinion, there is still room here for some more work and perhaps some superconductivity region in that regime of parameters. There is in fact a paper a couple of years ago by the also late and much regretted Sandro Sorella that actually documented superconductivity in that region. But the general overall conclusion qualitatively is that with T prime equals 0, it's really hard in the so-called pure Hubbard model to stabilize a robust superconducting ground state over an extended range of parameters. Okay, so T prime is actually not a detailed, is actually a very, very important perturbation. And again, this is something that many people in the community have known for many years, in particular from cluster DMFT studies, but also from the point of view of DMRG. This is a relatively recent paper in which the key role of T prime has been emphasized from DMRG studies. And the big news in this business dates from just, you see, a few months ago, in which in this paper in particular, it was demonstrated that when you turn on T prime, the competition between the stripe ordering and the superconductivity becomes now favorable to superconductivity, and the ground state of the Hubbard model at those value of the doping, and I think this was U8, but I forgot the exact number, does stabilize a superconducting ground state. For these values of T prime, which was up to 0.2, I think, this superconducting ground state did have also a small charge modulation. So these are coexisting charge modulation and superconductivity, and it remains an open question, which is under study these days, to see whether when you increase T prime, you can actually get to a pure D wave without charge modulation. This is an open question. Okay, so this is the good news in the field. There is robust high temperature superconductivity in the Hubbard model with a non-zero T prime, both in the hole doped and electron doped sides of the model. Okay, so let me here take a little bit of a sidebar, which is the question of how the stripe ordering melts as you increase temperature. So think about starting from the stripe ordered ground state, which has both spin and charge ordering, and increased temperature. Spin ordering breaks a continuous symmetry. So we know that because of Mermin-Wagner, it cannot survive 0 temperature. It will just be quasi-long-range order with a significant correlation length. But what about charge? Charge is breaking a discrete symmetry. So in principle, it should survive finite temperature. Surprisingly, this issue was not very much studied up to recently. And recently, we've put out this paper in which Bo Shao, who is a postdoc at CCQ in New York, studied this question using FQMC methods and concluded that, yes, indeed, there is a finite temperature phase transition above which the stripe is melted and below which the stripe is present in terms of the charge modulation. So there is a finite temperature transition to for the melting of the stripe in the charge order of the stripe pattern. And look at this temperature scale, which is in unit of the hopping. This is below what cold atom experiments can currently address, but perhaps not that much below. I expect that a new generation of cold atom experiments will be able to address temperature over hopping of the order of 0.2 to 0.3. So they are getting there. Okay, very good. So Incidentally, and this is again an illustration of the handshake, I wanted to emphasize finite temperature extensions of matrix product states and tensor network methods have now been able to also address this question of how the stripes evolve as you increase temperature. This is one way to do that is this so-called minimally entangled typical thermal state method, which is really a combination between sampling and so it has a Monte Carlo side if you want, but using the MPS encoding of wave functions. I don't have time to describe this method in detail, but let me show you some of the results. So this is the magnetic structure factor on long cylinders, which is what these methods can do, of width 4 in that case, but very long in the transverse direction, in the longitudinal direction. This is the magnetic structure factor. This is the charge structure factor. And I want to attract your attention to two things here. So this is the spin structure factor at wave vector pi pi in blue, and at wave vector, which is the stripe ordering incommensurate wave vector for the specific doping studied here in red. And what you see here is that there is an onset of spin correlation, which takes place at a temperature which is fairly high, of the order of 0.4 times the hopping. So fairly high, takes over. The guy which dominates here are the pi-pi correlations, so commensurate antiferromagnetic correlations. And then at some point, the incommensurate one take over. So you see this guy goes down at this temperature of about 0.1, and the incommensurate ones gain over the commensurate ones. And at that temperature in those calculations, the charge onset takes place. Okay, so the picture is that spin physics runs the show. There is an onset of spin correlations at a much higher temperature than charge. There is a regime of temperature where things are dominated by pi-pi correlations, which become substantial. And then only at a lower temperature, charge ordering takes place. Okay, so this is a beautiful example of this handshake thing. Okay, so I'm of course running out of time, but I want to tell you something about our understanding of the pseudogap in relation to spin correlations indeed running the show in that problem. So pseudogap, we heard about the pseudogap yesterday. You all know about the basic pseudogap phenomenology. You know that the pseudogap, originally discovered by NMR as a drop in the night shift as the system is cooled down in the underdoped regime, has been understood much better experimentally from a momentum resolve point of view. We know that the suppression of this density of excitations takes place at the antinodes, and that the nodes have relatively well-preserved quasi-particles in the underdoped regime. We know that from RPS. Okay, so there are a few outstanding questions in relation to the pseudogap. What is the physical mechanism? And is the Hubbard model a sufficient minimal model to account for the basic phenomenology of that pseudogap? Okay, so what do we know? We know that, again, spin correlations have an onset, which is taking place at a higher temperature than charge correlations. And we know from, in particular, recent calculations using the diagrammatic Monte Carlo methods, that the correlation length of the Hubbard model can be mapped out from these calculations, and it has, as you would expect qualitatively, a non-monotonic dependence on mu. So if you are at small u, you need to go to very low temperature to have a long spin correlation length, which will then explode exponentially. If you are at large u, you also need to go to low temperature because the characteristic temperature scale is J. And in between, there is a region which is harder to address, in which the correlation length has a maximum as a function of u. Okay, this is all documented very precisely for infinite systems in this work, which is now published actually. Okay, so spin correlations run the show, and we know that in the weak coupling limit, it is indeed spin correlations, but associated with a large correlation length, which are responsible for opening the pseudogap. we had a beautiful talk yesterday about this from Andrei Chubukov's collaborator, recent beautiful work, which also, I would say, puts a new development on something we've known for several decades, which goes back to Wilk and Tremblay, that in the weak, and also Andrei's work, that in the weak coupling limit, the correlation length grows as we go to low temperature, and this indeed destroys quasi-particle at the hotspots on the Fermi surface. So there is an analytical understanding of this. Two-dimension is crucial for this mechanism because it's associated with an infrared divergence of this integral. And recently, this multi-method, multi-messenger work that Thomas led when he was still in Paris actually has demonstrated that the qualitative picture behind the pseudogap formation, the weak coupling limit, indeed applies and indeed is confirmed and even refined by these computational results. In particular, one of the surprising things we found in this paper is that the exponential growth of the correlation length applies even in the metallic regime, which is something that was not fully explained by theory, and as we heard yesterday, is now explained by analytical calculation. So this also shows you how a feedback, a constructive feedback between computational results and analytical understanding can take place, because this finding was kind of a challenge to the theory. Okay, so pseudogap in the weak coupling regime, the box is ticked and everything is understood probably. So that's the take-home message. Pseudogap is due to spin correlations and only applies in the weak coupling regime when the correlation length is large enough. Okay, so what about strong coupling? So again, I'm kind of running out of time, but I would like to deliver the key message that we've learned from various methods about the nature of the pseudogap in the intermediate to strong coupling regime, both from a cluster DMFT point of view, and now also from a diagrammatic Monte Carlo point of view. And the message is that the spin correlations run the show. They are responsible for the pseudogap opening. Yes, the two-dimensional Hubbard model has a pseudogap in that regime. And in contrast to the weak coupling regime, that pseudogap does not require a large correlation length to open. And this is kind of a challenge for analytical theory. I don't think we yet have a full analytical understanding of this phenomenon. There are various proposals, including by people in the audience, but we don't have a full understanding of that. Although computationally, I regard these results as established. So let me document that. The first kind of handshake that demonstrated that, we've known that from cluster DMFT for many, many years. Emmanuel Gull, for example, who is somewhere in the audience, and many other groups in the world have actually documented that already 20 years ago in cluster DMFT calculations of various kinds. But this paper here established a handshake between diagrammatic Monte Carlo methods in the infinite volume limit and cluster dynamical mean filtering in the DCA version, carefully extrapolated to large cluster size. And let me, so this is the work of Wei Wu when he was a postdoc at Collège de France a few years ago. As I'm very briefly, the thing I would like to say is that these cluster methods, for example, amount to discretize the Brillouin zone into patches in which you're going to approximate the self-energy as being constant over a patch. If you are able to do that and extrapolate to infinite cluster size, which means arbitrarily fine patching, then your method becomes controlled and eventually exact. And in this paper, we've been able to achieve that, admittedly in some specific region of parameter space, but below the pseudogap scale. Here, what you see is the imaginary part of the self-energy along this path in the Brillouin zone, both obtained by diagrammatic Monte Carlo, which is the bit old school diagrammatic Monte Carlo. The field has progressed a lot since then, as a function of momentum, compared to size extrapolated DC results. And you see that there is quite good agreement. And you see that the scattering rate becomes very large. The imaginary part of the self-energy becomes very large when you actually cross the antinodal region, which is the thing that opens the pseudogap in this system. Okay. In this regime of strong coupling, the notion of hotspots is not really relevant. The whole region near the antinodes becomes incoherent and pseudogap. Okay, very good. So what about understanding? I'm going to skip some of that. There's been beautiful, because I'm running out of time, there's been beautiful comparison to experiments, both in calculating the night shift and also in part the neutron spectrum, which display this characteristic maximum of the night shift as a function of temperature in the pseudogap regime. Okay, so what about the mechanism? A few years ago, there was a beautiful technique introduced by, including some of the organizers of this workshop, which allowed to interrogate your numerical calculations and ask in which channel is the action. So I don't want to go into the details of how this is done. This is really doing some sort of surgery of the self-energy. It goes under the name of fluctuation diagnostic. And what these methods have established, both first in the context of cluster extensions of DMFT, and then also in the context of diagrammatic Monte Carlo, is that indeed the scattering processes which are responsible for the pseudogap opening are taking place in the spin channel. So this is from DCA, and this is from our results. Oops, sorry about that, of diagrammatic Monte Carlo back in the day. Okay, so the take-home message of the strong coupling pseudogap is that, again, what opens the pseudogap are spin correlations, but that in contrast to weak coupling, a large correlation length is not required. And a correlation length of like 2-3 lattice spacing is enough to open a pseudogap in that regime. So that's qualitatively different from weak coupling physics. And to a large extent, this is still waiting for a proper analytical theory. Okay, so I will end the talk by reporting on some really recent results in which we address the infamous question of what is the fate of the pseudogap as you cool down to low temperature, because we need to reconcile this picture of a pseudogap opening in this temperature range of, say, 0.4 down to 0.1 or something, and then the statement that the ground state can be stripe ordered. So we addressed this in recent work led by Fedor Simkovic, Ricardo Rossi, and Michel Ferrero. And what we did, so this is CDET version of diagrammatic Monte Carlo. What we did is we mapped out as a function of U and Hall doping. And again, here, this is for the infinite volume system. So these are completely controlled results. We mapped out the region where there is a pseudogap. And by the way, this is a contour line of the correlation length. So you see that here we have a pseudogap with a correlation length, which is only a couple of lattice spacing. And we did this or these people did this for a number of different temperatures. And they attempted bravely to extrapolate their results to low temperature. So what you see here is the pseudogap region in red, which is invading more and more of the phase diagram. And eventually, where the method sort of breaks down at this temperature, which is not that high. As you see, this is quite a success of the theory. But what Fedor and co-workers attempted is to extrapolate these results to t equals 0. And when you do that, what you find is this. Namely, these are the different pseudogap boundaries for different temperatures. The red line here is the extrapolation. Of course, there is some arbitrariness into this extrapolation, which is this red ribbon here, to t equals 0. And what you find is that the boundary between pseudogap and no pseudogap extrapolated to t equals 0 coincides quite accurately with the boundary between stripes and no stripes. So for t prime equals 0, the conclusion of that work is that eventually, as you cool down, the pseudogap state is unstable to stripe ordering. And that answers one of the questions in the field, which has been with us for many, many years. And of course, a key challenge is to extend these results to finite T prime and understand whether that statement is very general and what happens at finite. Okay, so this is the picture that emerges from this. High temperature, some sort of soup. There is an onset of antiferromagnetic spin correlations at T star. This opens a pseudogap. At some point, there will be charge ordering as demonstrated in this work, and the ground state will be stripe ordered and possibly superconducting in some region of parameters. Okay, that's the end of the talk. Sorry to have been so long. I hope I convinced you that there is progress in the field. And I'm so optimistic about this that I really believe in the coming few years, we'll have finally dissipated most of the fog about the status and the physics of the two-dimensional Hubbard model, thanks to a community-wide effort using many, many different methods.